Hey, good morning, everyone. I'm Shizu from Jacobs. My presentation is a recent case study about dynamic signal management. Two of my colleagues worked on this case study with me, Zalan and Shanka, but unfortunately they were tied with other business, so cannot make this. Okay, this is the presentation outline. After the overview introduction, I'll talk about the methodology of the signal controller operation under different traffic scenarios. The next part will be how we develop web controller in Vissim and use COM API to run it. The Vissim simulation were conducted with different signal management, and the results were compared to each other. Okay, so on the highway with synchronized intersection, most signal controllers store the multiple timing patterns to serve the different traffic conditions. The signal patterns would be switched from one to another according to certain rules. Traditionally, the pattern switch follows the pre-scheduled timetable, which usually are designed by time of the day and day of the week. This is an example of the timetable. The patterns will change at these fixed time points on certain days, no matter how the actual traffic conditions are. With the timetable, the signal operation is expected to serve the peak and off-peak period with different timing patterns. However, as it's based on historic data, so it would be more suitable for those regions where the traffic pattern is relatively steady and typical. If the traffic flows constantly have inconsistent change, the scheduled switch cannot instant respond to the traffic condition and would not be effective in managing traffic flows. In such scenarios, the dynamic signal operation would be more appropriate. It can better serve the fluctuated traffic patterns and irregular traffic flows by responding to the real-time traffic conditions with streaming of sensor data and artificial intelligence algorithm. So to evaluate the dynamic management of signal controller, we conducted the Vissim simulation to compare the two types of signal pattern switch. The simulation modeled the traffic network of an East Coast beach area, including an 8-mile-long arterial and several major intersecting roads. All signalized intersections on the major corridor belong to a same responsive zone. That means all these signals are coordinated, will switch the signal pattern together and have the same cycle length at the same time. For the beach area, usually the summer traffic volume are more than double due to the vacation travelers. The typical weekend peaks usually span several hours during the whole daytime. In addition, the commercial and residential land use along this arterial generate a large number of pedestrians in this case. The crosswalks at the intersection and middle segment cause additional interruptions to the traffic flows. This unique challenge asks for more instant and effective response from the transportation management system. This part is the introduction on our methodology in this case study. Two parameters were used in dynamic switch to decide whether the signal pattern should change or not. They are both based on the real-time traffic data collected by detecting sensors at certain intersections. The V plus O is used to determine the cycle length. It's calculated based on the per lane vehicle volumes and occupancy rates in each time interval, and then is aggregated by direction. The V value measures the directional traffic flows to identify the congestion direction. In this zone 20, there are 7 intersections designated as the triggers. providing the sensor data to calculate the V plus O and the V value. So from the figures, we can see the squares where the under pavement detectors are installed. They're all located on the downstreams of the intersection, downstream lanes of the intersection. Every 5 minutes, they count the number of passing vehicles and the time duration when they are occupied by vehicles. This equation shows how to calculate the per lane V plus O through the whole corridor. For one certain lane, the volume and the occupancy were collected from different intersections and then aggregated together. So for each direction, we would have 3 per lane V plus O in this case. There are 3 lanes, the 3-lane arterial. And eventually, the per lane V plus O would be averaged by direction, so we can get a 2 V plus O value every time interval. And this parameter is used to determine the cycle length of the next time interval. The switch threshold are value ranges. This model used 3 threshold band. You can see this blue rectangle from dark to light. This flowchart shows the changing logic and the rules. In this example, the cycle length was 90 seconds during the midnight, and in the morning 6:40, the northbound V plus O, the orange line, reached the upper bound of the first threshold band, which is 8. So the cycle length changed from 90 to 120 here. And around 8 a.m., southbound V plus O passes the entry line of the second band here. So the cycle length increased to 150. And about 2 hours later, the cycle length changed to 165 when southbound V plus O reached 40, the entry line of the third band. And the 165 cycle length continued to the evening. So you can notice around 7 p.m., even though the southbound V plus O dropped to about 28, less than the X line of 30 of the third band, but because of the northbound V plus O is still high. So the cycle length keep unchanged, still 165, until about 9 p.m., both northbound and southbound V plus O drop to less than the 30, the entry line of the third band. So the cycle length changed back to the 150. So this is the changing logic and the threshold for the V plus O cycle length. So after the cycle length was determined, the selection of the offset and phase splits refers to the proportion of directional volumes represented by 3 levels of directionality. And with 90 and 120 cycle lengths, only the default level is used here, which assumes there is no significant difference between northbound and southbound volumes. But with the 150 and 160 cycle lengths, the V value is calculated to identify the congested direction. It averages the volumes collected by all detectors on the same direction and find the southbound volume percentage of the total volume. And this table, this matrix table, the first column is the current level of directionality, and the first row shows which level it would be in the next time interval based on the V value threshold here. And this part, I will present the signal control development, including the web controller and the Vissim application. We choose a web controller because in Vissim, the RBC controller, we cannot change it by the COM API. You have to follow the pre-coded schedule. So The VAP is a traffic-dependent program enabling Vissim to simulate vehicle-actuated signal control. It can be created in Vissim. In the controller editor window, certain basic common parameters can be defined for all the patterns, such as yellow time, red time, minimum green, and more data, including pattern details, are stored in external text file, as well as the program logic. So the signal data file PUA contains 3 sections here. So they define vehicle and pedestrian signal groups, describe which group are in the green or red interval at a certain moment, and designating the first operation status. The information defined in the PUA would be applied to all signal patterns. The VAP file describes the program logic with a simple language. It also contains the signal data that isn't defined in Vissim or in a PUA file. In this example, there are 9 signal patterns with 6 phases for each. You can see from these arrays, the phase 3 and the phases 3 and 7 are actually empty. And in this intersection, in this case, the correlated phases are 2 and 6 with minimal recall mode. And they don't have vehicle detectors for this through movement. The numbers in each area need to be modified for each specific intersection. And to make the signal operation correspond to the traffic condition, we developed a Vissim COM application with Python. The application uses Vissim event-based script. It includes 3 major steps. You can see the red underline comments. First, it captures the traffic data and calculates the parameters, and then compares them to the thresholds. After the target pattern is determined, the comments would be sent to the web controller to do the selection. The application requires 5 external input files in total. So here are some examples. The first one, the top one, is the V+O threshold. And the middle one is the list of all pre-coded signal patterns in this network. And the bottom one is a list of trigger intersections. So not all the intersection providing the sensor data. The COM application does all these input files. You can see the zone attributes, because for the future implementation, it could be applied to multiple zones. Although in this case, only one zone, we only test on one zone. The COM application doesn't export external outputs. So all MOEs used for evaluation will be collected by Vissim itself. Okay, so this is a simulation. We simulated 12 hours traffic on the summer Friday, plus 1 hour seating time. 3 scenarios were modeled and compared. Scheduled scenario used a fixed timetable. Signal patterns change at preset time points. The responsive scenario switches the pattern based on the V+O and the V value of current time interval. The predictive scenario used the same logic to switch the pattern. Only when calculating the V+O and V value, the COM application would use the forecast volume and occupancy provided by AI-based ITMS system. The vehicle input were loaded in 15 minutes interval, and the volume and the volume and the occupancy rate were captured every 5 minutes by the data collection measurements. They were coded at the downstream links of the trigger intersection. 3 MOEs are used for evaluation. This is a summary of the result. Regarding the served volumes in the model, the three scenarios had similar operations, no matter the average hourly volume along the corridor, the upper one, or the highest hourly volume. The three scenarios had numbers close to each other. But for the intersection delays, the dynamic pattern switch can generate better operation. This left chart summarized the number of intersections with a different level of service. From 3 p.m. to 8 p.m. is the most congested time on Friday. During this period, two dynamic scenarios show more intersections operating at level of service A, B, or C, and less at and fewer at level of service F. In the meanwhile, the dynamic pattern switch can improve the corridor travel time as well. So this is the comparison of northbound travel time. The travel time was averaged every 3 hours. For each sub period, the scheduled operation had the longest travel time, the dark red one. And the dynamic scenarios shortened it, especially with the congested traffic condition. The more severe the congestion is, the more significant the improvement is. Like this chart in the afternoon time, this is most congested period. And for all sub-period, we noticed the two dynamic operations have the travel time very close to each other. And similarly on southbound, the travel time curves of these two dynamic switch were almost overlapped. And compared to the scheduled operation, again, the greatest reduction also happened when the congestion is the most severe, the afternoon time. Okay, so from this case study, we can see that dynamic signal pattern switch can improve the traffic operation because the especially under the severe congestion, because the dynamic change can respond to the real-time conditions more quickly and effectively. However, between these two dynamic switches, we haven't seen significant difference yet. This may be due to congestion level or how long in advance the predicted traffic data is provided. So one of our next steps would be sensitive analysis. We will test various demand and different forecast term. We are also going to validate the model scenarios with other data sources, like on Saturday or Sunday, or from another beach network. Meanwhile, the operation of the predictive scenario would be impacted by the accuracy of the short-term forecast for the future time interval. Improvements of data collection and AI algorithm would be contributive to the predictive scenario. Okay, that's it. This is my presentation. Any questions?